and Jonah, our presenter tonight.
Thank you. Thanks. All right, let me connect my computer now. Okay. Cool. Hi, thanks for coming. I'm Jonah. So I work at Columbia. My primary work is on STAN, the probabilistic programming language. Just out of curiosity, it's not the topic of tonight's talk, but are there people here who have used STAN or know what it is? Okay, cool. For those of you who don't, although most of you seem to, modeling language for fitting statistical models that interfaces with R and Python and other platforms. But I'm not going to talk too much about STAN tonight. It's what was used to fit the models that I'll show. But the point of my talk tonight mostly is to talk about workflow. And I'm going to use visualizations and pictures to try to, but the focus is really not on like, new fancy visualizations. It's just on the workflow and how you can use visualizations at each step in that way to hopefully get a better grasp of what's going on and fit better models. Some of the particular models that I'm going to talk about are Bayesian models, but a lot of the ideas are more general in terms of the workflow. Although if you're not using Bayesian statistics, you can kind of ignore a few of the parts that you'll find. But otherwise, I think it'll be more broadly applicable, or at least I hope. All right, and please feel free to interrupt with questions. Like, I'd rather talk about it in the moment, but then I'll also leave time at the end. But it's totally fine to ask a question in the middle. Okay, so I said I'm mostly going to talk about workflow, and I'm going to talk about some steps in this workflow that I think will be familiar to everybody in the room, like, sorry. You might know it, prior predictive checking. This is where, and I'll go into more detail, where before we actually fit a model using real data, we can already assess, what type of data does the model we're considering generate, right? And think if it's consistent with our domain knowledge, and before we even bother using the real data that we have. Then you end up fitting a model. Depending on what types of algorithms you're using, there's going to be different sorts of diagnostics. Hopefully you're using algorithms that have diagnostics. And so there'll be a step in your workflow where you're fitting potentially many different models. In the Bayesian workflow, what we would do afterwards is actually check the fit of those models. And to do that, we would do something called posterior predictive checking. But there are analogous steps where you're checking the fit of your model outside of Bayesian statistics also. And then finally, or at least finally for this talk, if we have time, you might have many models that you're considering. You want to find some way to compare them, select among them, average them, something like that, right? And then the idea here would be then to iterate on this process, honing in on kind of the most useful thing that you can do for whatever problem you're studying. So it's not that you would stop here. Often at some of these steps, you might identify things that you immediately notice you want to make changes to, and then you don't have to keep going. You can kind of come back to the beginning, starting at any point, and go through. And the idea is that you're kind of moving towards whatever model or collection of models you'll end up using for the problem that you're working on. And so that's the workflow that I'm going to talk about, and I'll go into detail at each step and show some pictures, and I'm going to use one example, kind of running example throughout the whole thing that is not from my area of expertise and probably not most of yours, but I think is a good kind of simple example to use, and I will go through that next. I should give credit to my collaborators on this. And I'll share these slides. I think they share them through the meetup page or something. And so these are links if you want the code for making the stuff that you see or to read the paper that we wrote on this topic. I think those, I'll check and make sure those are the right links when I share the slides there. But this is work with Dan Simpson, Aki Vetteri, Michael Betancourt, and Andrew Gelman. So definitely not just me. Okay, so the example that we're going to use is estimating the concentration of particulate matter, so a certain type of air pollution, and really small particulate matter, in this case measuring less than 2.5 micrometers in diameter. And so this is, I think we cite some, or point to some references in the paper, but this is a concern globally, to different degrees in different parts of the world. It's associated with deaths of not just animals, but also humans on a pretty large scale. And there's a problem, which is that we only have good data in certain parts of the world. So most of the data that is collected on this, and primarily I'm going to be talking about data that's used by like the World Health Organization and other big bodies like that, come from satellite measurements, whereas ideally you have measurements from ground monitors. And so for the purpose of this talk, if I talk about the actual concentrations, I'm basically referring to like ground monitor levels. We'll just kind of, there's some kind of measurement error there, but I'm just going to kind of treat those as known. It's the satellite measurements that tend to be very noisy, right? And unfortunately, the distribution of like where we have the ground monitors in the world might not be too surprising to you. They actually tend to be, I'll explain it, not located where we think there's the highest, the largest problems. So on this picture here, the black areas are where there are ground monitors for measuring the concentrations here. And the darker pink and purple areas are where there's the biggest problem, right? So we have very sparse coverage in Africa, even though there are really high concentrations in Northern Africa, also parts of Asia, but most of the monitors are in North America and Europe. Okay, does that graph make sense? Okay, so that's the problem. What we basically wanted, the problem to solve here is how can we use the ground monitor measurements? So for some locations, we have both satellite and ground monitor measurements, so the black dots essentially. Can we use that information to better calibrate the rest of the satellite measurements where we don't have ground monitor measurements, right? And this is not a problem that I solved or that we solved. This is a problem that other people were working on, and we decided to use it as an example to talk about the workflow. But there's a good paper where they actually fit more complicated models than we'll talk about today, and that's linked to in the paper that associates this. So if you actually are interested in this problem and want to see what they're actually really doing, you can check that out. I think the only thing that I have to say about exploratory data analysis that might not be the most common thing that's said there, like that might be new, but probably not to most people, is that to think of it as a step where you're already building, I think I could say building a network of models, where you're already using the exploration to imagine models as opposed to just saying, okay, what features of the data are there? And so what I mean by that is stuff that you've definitely already seen. If I say, okay, like there's a linear trend here. So what you're looking at here is on the x-axis, the satellite measurements, or the logarithm. This is all going to be on the log scale. And then on the y-axis, the ground monitor measurements, obviously just for the locations where we have both. And the different colors are the different regions. The World Health Organization groups, the regions are all geographical except for the high income region, which is a combination of North America, Europe, Australia. And you'll see on the maps in a second. And so if you just plot these on a graph, and I think I just told ggplot to overlay a regression line, and the R squared is like 0.6 or something like that. And it's actually a pretty decent linear fit, but you can also notice immediately that probably there's variation by region here, right? And so that would be something that you might notice in any exploratory data analysis, but I'm thinking immediately when I notice that, okay, I'm probably going to fit some sort of multi-level model here where I'm allowing for, you know, heterogeneity across the regions and also going to partially pool information to make up for really small sample sizes in some of the areas. So I'm already kind of imagining the models that I might fit. And so then I just made another plot. Well, actually, first I showed you the World Health Organization regions. So the pink ones, does this have a pointer? You can see that Australia, like Argentina and Chile and Western Europe and North America are all considered one region, but then everything else is geographically contiguous. And so if you make the same plot as I made before, but you put a different line for each of those regions, you can see, so these are kind of like uncertainty bands. And again, I'm not fitting, well, technically it's fitting models, but I'm not really fitting models here. I'm just telling ggplot to like put the regression lines here. I'm just improvising a little bit. I'm not really in my model fitting stage here. I'm trying to look at what's going on in the data. And so you can see the ones with the larger uncertainty bands are going to be from the regions where we have less data points, right? Or also where we have more variation, either one. And then, but so some of the lines are pretty precise. Some of them, there's a lot of uncertainty. The slopes and the intercepts are different. Now, I might not believe that it's true to this extreme. So we don't really know what the slope and intercept of this line is, for example. But there is evidence here that I should think about fitting a more complicated model than just a regular linear regression or something. So the first thing we did was we said, well, why are we grouping countries in this way? Well, we didn't do this, but we had the idea to do this based on some work by other people that we linked to in the paper. And so if you, I want to show back up at the top here. So if you cluster countries based on like, you know, past information about what we know about the particulate matter concentrations, then you get a different map, right? Some parts of it are similar, but you also get a different map, which means you have a different way of grouping the countries to fit a model, and you'll learn something different if you're estimating group-specific or country or region-specific effects or something like that. And so you'll probably learn something different depending on how you group these countries. And so you can see that we get different lines, right? So already, I'm just kind of making quick plots here, but I'm already imagining like 3 different models. One is like a simple linear regression that I don't think is, that I don't think is particularly useful, the one we saw here, but I'm probably always going to fit the most simple model anyway, at least so I can then look at where it does poorly and build it up. And then here you can imagine like 2 different models where we have observations nested within regions, but the regions are defined differently, right? It's kind of 3 different models already. Any questions on that so far? So that's nothing new, I think, for the most part. Okay. To be if we have j different regions and n measurements, then this is the simple linear regression model. So just with all the variables on the log scale. So we have like 1 intercept and 1 slope, and that's the normal distribution. So that's like a simple linear regression model right here. And then, sorry, is this notation okay for people? Okay. Everybody uses different notations, so sometimes I get confused myself. And then the other 2 models are the same, except the slopes and the intercepts are going to be allowed to vary by region, and the only difference is how you define the regions, right? So we would have, I'm going to use mu here just so I can then define it on the next line, where now we have some kind of global intercept here, alpha 0, some shift off of it for each of the j regions, right? This gives us a unique intercept for each of the regions. And then we do the same thing for the slope, where you have some slope for some kind of global slope, and then a region-specific deviation from that slope, right? So far, I actually haven't really said anything Bayesian at all, right? So.
Are you saying all the variances are the same in every?
Yeah, in this particular model, we're assuming that the variances are the same, but you can generalize that too. And in fact, I think so the actual model that ends up getting fit in the real analysis of this that we didn't do is like, there's spatial correlations and all sorts of stuff like that. But for the purpose of like thinking about the workflow, we just stopped here. But yeah, you'd probably fit a more complicated model than this. Good question. Any other questions? Sorry, I'm a little short on breath too. I'm just getting over a cold. I feel like I'm panting a little bit. It's weird. Okay, right, so these two terms are going to combine for the intercept, and these for the slopes. I could have just gotten rid of the alpha 0 and beta 0 because it's the same for everybody, but I like thinking about it as some global intercept and then a shift for each of the regions. Okay. But, right, we can take this a step further and say we're going to, well, I like to say we're going to model the slopes and the intercepts, right? We could have other variables. We don't in this particular model. We could have other variables that help us learn about the slopes and the intercepts, but at a minimum, we can give them prior distributions. In some sense, we're not, so here we're going to say that what we're going to say ahead of time is that they're centered at 0, right? In other words, we could have also dropped this alpha 0 term and stuck it in there instead. The deviations from the global slope and intercept are centered at 0. And then there's some amount of variability, in this case tau, that's saying like how different are these intercepts from each other? How different are the slopes from each other? How much are they allowed to vary? Right? So if tau alpha is really big, then the region intercepts are allowed to be very different from each other. And if it's very small, they're going to be they're very similar to each other. And the same for the slopes. In the extreme, I mean, they could be identical to each other, right? But so this is what's going to, but the fact that we're not fixing the value of the taus, we're going to estimate them. We'd need to put priors on them too. But we're going to estimate them means that we're going to get partial pooling in this model, right? The taus are going to be informed by all the data points. The alphas correspond to each region and the betas to each region, but the taus are common to all of them. So we're going to learn something about the variability that way, which is going to pull the estimates of the alphas and the betas towards each other. Does that make sense here? So in other words, for the observations for the regions where we don't have a lot of data, right, we're going to be more suspicious of the estimates that we get, and we're going to want to use more information about what we know globally, right? And for the regions where we have a lot of information, right, we can be more confident about what we can learn just from those data points, right? And that's pretty much true of like every phenomenon I've ever studied, right? That something like that is the case, right? You have more information on certain groups, whatever group means in what you're studying, than on others, and you're going to trust what you know about the groups that you have more information about. And so if we just put if we drop this entirely or just fixed these values, we wouldn't get that effect, right? We would just be saying that the slopes and intercepts are totally independent of each other. But here, this links them together. They're all dependent on tau, which means that information, if you drew this out in a diagram, right, you'd be able to connect all the observations to tau, right? Maybe I should have drawn that. And that's what's going to give us this sharing of information. And you'll hear people say shrinkage or borrowing strength or partial pooling, right? Does that make sense? Question about that topic? Oh, cool. Okay. This is my favorite part of this because we get to just like simulate data and do stuff. But I think for a long time I didn't realize just how important this step is. This saves you a lot of time, and that is get to know the models that you're thinking about fitting before you fit them, and you'll see what I mean in a second. So if we use, I'll say that if we use proper, just imagine we're going to use proper prior distributions here. That what if you're going to fit a Bayesian model, what you're really saying is that I have some joint probability distribution over everything that's observed and everything that's unobserved, right? All the data and all the parameters, or we say data and parameters, it's really more broad than that because parameters can include like missing data points and things like that, anything that's unobserved, right? And you can write that either as like a likelihood times a prior or a posterior times a marginal likelihood. The middle one is the one that's actually useful. Often we're trying to find out the things on the right-hand side. And these we get the likelihood and the prior we can actually specify, right? And so what this means, because we have a joint distribution over data and parameters, if we use a proper prior distribution, this model can simulate data itself. I'll show you what I mean by that. I'm going to skip this piece here. So we have to disallow improper priors because you can't sample from something that's not a probability distribution, right? But if we're not using flat priors here, then a Bayesian model will be generative, which means that it describes a process by which data can be generated. And so this is what I mean by that. It's often very hard to write down the whole data generating mechanism, right, as one function, like what's the distribution that, right, we can often, I should say, we can write down pieces of what we want to know and piece them together to get something useful. And those pieces are, we have some prior, and so we could simulate some value for our parameters. I'm going to call the particular value theta star. So we just say we have a normal distribution. That's our prior. We just sample a value from that distribution, right? And then we have a likelihood, which could be whatever. Maybe it's a Poisson distribution. In the case of the particular matter example, it's also a normal distribution. And we can simulate observations, y star data points from that, right? So we have this two-step process. You draw a value from the prior, plug it in to the, in this case, the data distribution, right? The distribution that's generating the actual measurements. And from that together, it's as if we drew data points from the full data generating mechanism, right? But we often don't know how to write down this P of y. But we do, well, it's not that we know the other parts, but we can choose the other parts, right? And to do this, this is the same process that we'll talk about with posterior predictive checking, but here instead of plugging in, instead of using like actual data points, we're just generating them, right? Generating them using draws from the prior first, as opposed to like learning those, right, from the actual observations, and then simulating data points using the posterior of theta or something. That's what we'll do later. So, but I just want to emphasize again, at no point here have we actually like plugged in the data points that we'll end up using to fit the model. We've simulated data points that, if our model is worth fitting, should be somewhat consistent with our knowledge of whatever we're studying, right? And so the point is that if you pick, and these are just some like kind of standard non-informative priors that you might see in like a literature. Here I'm using a normal distribution with standard deviation, not variance. But it doesn't really matter what you pick here, but like, you know, vague priors that don't really convey any domain knowledge. If we think about our particulate matter example, so on the x-axis of this plot are the ground monitor measurements, like the full set of them, not differentiating by region, just the full plot. And on the y-axis is our data points simulated using these priors for some of the parameters, plugging them in to the normal distribution for generating the data points, and then I plot them, and they are kind of ridiculous, right? So we have like multiple orders of magnitude difference, and we're on the log scale here. Now, I'm not suggesting that you should always compare to your observed data at this point, but since we're not all experts in particulate matter, it's helpful to look at that. But if you're actually studying a problem, you don't need to, at this point, use your actual data and make this explicit comparison. You should be able to make these simulations, look at them on their own, and say, that's totally inconsistent with my domain expertise or something, right? With my prior knowledge. But in this case, it's nice to look at them both because we're not the people who would actually be doing an analysis of particulate matter. But, right. So if we were to use priors like that, right, so we haven't used our data yet, right? So if we were to use priors like that, then what would that, right, how could we get useful results using priors like that if the simulations of the data that we're getting are so ridiculous? We could, but really only if we had data that was informative enough to totally wipe out the effect of the prior distribution, right? Particularly when we're fitting like a hierarchical model like this, well, we already know in this case that we have noisy data, so that's probably not going to work. But in general, even if you have a lot of data, that doesn't mean that you have incredibly informative data, right? It's not about the number of data points necessarily. And especially then if you're slicing it up and fitting models that are dividing, I don't know, people into subgroups or products into other groups, and you're making smaller and smaller groups defined by more variables, then your data actually becomes pretty sparse, right? If you're trying to answer any particular kind of fine-grained question there, right? And so people didn't used to like care about this, right? Like this idea that you should, I mean, people used to even use, I don't know, for a long time, people didn't really ask, well, what happens if, is the data that I get if I simulate from the prior distribution and plug it in at all consistent with, with what we know? But I think more and more this is becoming common practice in a particular like subset of Bayesian statistics. But I think the principle can be applied regardless of if you're doing Bayesian work or otherwise, just to think, like, to assess the implications of your model, right? You don't need your actual data to do that, right? And then why bother fitting that model if it's already totally implausible? right? Unless you want to just learn from it. So if we do, if we do something more reasonable, which is to say, let's, if you talk to people who study the particulate matter problem, they'll tell you, well, the satellite measurements are noisy, but like we would tend to think that they're not necessarily particularly biased. Maybe a good prior at least is that like a slope of 0, an intercept of 0 and a slope of 1 or something like that as a prior, but then allow for to be wrong, a decent amount of variation around that line. And so these are just the priors on the global intercept and the global slope, right? So an intercept centered at 0, a slope centered at 1. These are the positive half normal distributions. You could use some other distribution there just for simplicity. You just need some sort of positive only distribution on the standard deviations of the intercepts and slopes that decays relatively quickly. And now remember, we're on the log scale here. So the actual measurements might be kind of like, well, we're dealing with pretty small numbers actually here. So these ones in like the standard deviation of 1 is actually pretty big. In fact, we'll see that these are actually pretty weak priors still in this case, right? So this might be a highly informative prior in a different problem and be totally unreasonable or reasonable, I don't know. But in this case, here's what you get if you simulate. So again, we have the actual ground monitor measurements on the x-axis just as a reference point because we're not experts in particulate matter. On the y-axis, we have the simulations that you get if you use these priors. Again, but you could use something just that has a similar effect. You don't have to use these exact numbers. Right, and then there's the next level of prior that's on the intercepts and slopes where these values are just getting plugged in. And you get data like that where, and again on the log scale being kind of twice as high up here as it is over there is a pretty big difference. You can see that these simulations are actually, and then if you are a domain expert, you'd say, okay, well, some of these simulations are actually consistent with like states of the world that are not possible given that life continues or something like that, right? Particularly these simulations. Like once you get up here, actually I think not pictured on the y-axis because it's too small is like the log density of like a neutron star, which is like 60 or something, I don't know, right? Like, so these are consistent with like no possible life on Earth or anything like that, right? But even some of these are too, but again, but this is much more reasonable, and if you were an expert on this problem, you wouldn't need to compare it necessarily to your actual observations. You'd just be able to say, okay, well, this prior data generating process covers like all plausible data sets that are consistent with our knowledge, right? It goes beyond that, so maybe this is like a conservative prior to use to say, I'm still allowing for data sets that I don't think are possible, but I'm not wasting computation, I'm not allowing my inferences to be affected by putting prior weight on things that are totally inconsistent with our experience of the world, right? And it does matter, right? You're going to waste computation time. If your data isn't super informative, then you're going to need to craft a prior distribution that at least constrains your inferences somewhat here. And so if you put them on the same graph, the more reasonable ones basically look like a line because they can't even fit on the screen. Right, so those are those two simulations here. And so again, we have used some of our actual measurements just to give ourselves a reference point. But if you were actually doing this analysis, you wouldn't have needed to use your actual data points to get this far. All right. And so just to, I don't know what time just to put this more into context, so this is right. So this is the stage of where you're essentially examining your own plan in some sense. Okay, I have these models that I'm thinking about fitting. Are they already, before I fit them, worth using, right? And I think that's an important question to keep asking. I'm going to actually jump ahead to, I'll include all that stuff here in those slides here, but the important one here, so then we fit these models. So we fit the 3 models that I talked about in the earlier slides. We used STAN and MCMC, and some of the previous slides are some diagnostic plots, but the most interesting piece here is to then do the same thing that we did with the prior predictive checks, but this time instead of simulating from the priors and then plugging them in to the distribution for generating measurements, we're going to use simulations from the posterior distribution, from what we've learned about all the unobserved quantities in the model, conditional on the data that we've actually fed in. So now we've said, okay, we're not using the prior anymore, but the process is going to be exactly the same. We're going to do exactly the same thing, but at the step where we sampled a value from the prior, we're going to take it from the posterior distribution. And what that gives you, if you do that 2-stage process again, is the posterior predictive distribution, which is essentially the probability distribution that you would use to predict new observations. Well, integrals are not fun. Sorry. So the process here is exactly the same. The only different part here is that now this distribution is conditional on the actual data. So if you run STAN or something like that, these would just be the samples of your parameters that you get. Or you run any MCMC algorithm or approximate inference algorithm that then can generate samples or something like that. And then again, we plug into the same distribution as before. In the particulate matter case, it's a normal distribution. We're saying that the log of the particulate matter is normally distributed. But whatever distribution it is here, binomial, Poisson, whatever, you're doing the same exact thing as you did in the prior predictive checking section, but just using samples from the posterior. And what that gives you is samples from the posterior predictive distribution. The difference between this distribution and the one in the prior predictive checking is that that wasn't conditional on the observed y. The squiggle here, oh, I meant to use star, sorry. Y star or Y squiggle or something, some new data point, right? Now we get samples from the distribution of what our model predicts, right? After learning from the data. And so here we actually make all sorts of different visualizations that are going to help. And some of these might be familiar to some of you, some of them won't be. But so here we can compare, we get to simulate as many data sets as we want. Sample we draw from the posterior distribution could then be plugged in and give us a whole new data set, right? So we can actually, let's say we take, I don't know, 5,000 samples from the posterior distribution. For each one of those, we could do this 2-step process and simulate a whole data set. And so we could actually get 5,000 simulated data sets, right? So each one, let me say that again. So I should have said this. Here, the theta, in the particulate matter example, theta are all the slopes, intercepts, everything like that, the error standard deviation, sigma, right? Everything that we don't know and we're trying to estimate. And then the y are going to be log particulate matter concentrations, right? And So each theta, so each intercept that we draw from the posterior distribution, right, we could simulate a whole set of y values, a whole set of measurements, the same size as our actual data set, right? But then we're going to simulate like 5,000 slopes and intercepts or something like that. So for each one of those, we could simulate a whole data set of particulate matter values. So then we could start making visualizations about what's the distribution of those simulated data sets. And so here, now we can say, how well does it fit the data, right? So what you're seeing here is a comparison. The dark lines are like kernel density estimates of like the actual data set, the particulate matter observations. And then these kind of shaded areas are actually like a couple hundred thin lines, thin kernel density, each one a different predictive, different sample from the predictive distribution. If you use Stan or something like that, you could generate these in the points that are used in like the generated quantities block or something, right? This is taking the kernel density estimates of a bunch of predictions, and you can see. So here, this is like we're looking at the whole data set distributions here. You can see the difference in fit between the multi-level model and the single-level model. We don't necessarily want to capture every little bit of noise here in the data, right? Which might be a sign of overfitting, but we want at least a decent fit to the data. Otherwise, why are we using this model? We can look at other things. For each of the predictive data sets, the simulations, we could calculate like the skew of that distribution, if that's something that, essentially whatever you're interested in the problem that you're working on. You might be interested in how much variability there is in the predictions, or what the means are, or whatever it is that you're interested in, you can look at for each of the simulations. And so these histograms are made by calculating the skewness of, each data set that I've simulated. And then the vertical bar is like the empirical value of if I calculated it with the actual data. Right? So this is a comparison of the predictions that my model, or the properties of the predictions that my model is making, and the same statistic calculated on the observed data. And again, we don't necessarily need to always get it exactly right, but it should be plausible, right? We're not looking to capture every bit of noise in the actual data, but we want our predictions to be consistent with the data that we've observed. Right, and then you can do the same thing at a more fine-grained level. So this is by region, right? And again, we fit 3 models, but I'm just doing comparisons between some of the one multi-level model and one single-level model. Whereas now each of these little histograms is for a different region. And then we're looking at the median of the predictions. It's just different examples. And the idea is not that any one of these comparisons is necessarily useful in every case, but you think about what are the things that are important in what you're working on, and then, right, so maybe you don't care about the median, but you might care about something else. So you could look at, you might care, I don't know, what are the most extreme, how extreme are the predictions that I tend to get if you're working in some area where you care about what percentage of the time am I getting an observation bigger than some value or something like that. Like anything that you can, any function that you pass in like a vector of observations and it returns a single number, right, can be used in this case. So, you can calculate mean, standard deviations, variances, skews, right, skewness, whatever, you make up some arbitrary thing, whatever thing you care about, you can look at its value over all of the simulations in your posterior predictive distribution, and then you get a sense of, so this is giving us a sense of the uncertainty that we have. Like if you just look at the underlying histograms, that gives you a sense of, well, how much uncertainty do we have when predicting the median for this group, right? If you're predicting new data, so this is like comparing to the existing data points, but then you might want to make out-of-sample predictions, then you can't overlay the thick vertical bar, which is calculated from the existing measurements, but you could make the same histograms and summarize your uncertainty in predicting different aspects of the whatever variable in this case, it's the log concentration of particulate matter, but it could be the number of products sold or something. It doesn't matter. I'm gonna stop in a second. So the slides go further into model comparison and stuff like that, but I guess to focus on the posterior predictive thing, I'll share these slides, and they talk about other visualizations that you can make to compare models that they're also linked to sources that explain. Are there links? Yes, okay. That explain the plots. But for example, just the types of visualizations that you can make when you're comparing models, right, is these are actually comparing the two different multi-level models. We've calculated something called the expected log predictive density. For these purposes here, you can just think about it as measuring like how surprising each data point is to the particular model, right? And then we're kind of differencing them here, and you can see that essentially whether or not we're below 0 or above 0 is saying one of the models, the data point is more consistent with one of the models than the other, right? And we can look at that for each of the different data points. So I've colored them by region here, and so we might not say, okay, one model is better than the other. We might be able to say, if we're interested in this predictive task, this model is better. But if we're interested in a different task, this other model is better, right? There might not be one answer. At least here, it looks like one of the models kind of dominates in a few areas, but then they're pretty consistent in other areas, right? So you can look at predictive measures like that summarize predictive performance on the whole data set and like collapse this all to like one number or something. Or you can look at it point-wise and examine differences in how the models do, different ways that you can subset your observations. And this is just a visual example of that. Of course, there are just numbers underlying this, so you don't have to make the plot. I think it's helpful here. I labeled this as Mongolia. It turns out that, so we look at this plot and then we say, wow, why is one of the models doing like so much better on Mongolia than the other? Well, it's because like, I think it's in a different region in the two models that we're comparing here, right? Because the regions are defined differently. And also there's only one observation from Mongolia. So it's just a weird data point. If we didn't know that in advance, if we look at this plot, we immediately say, okay, we should probably look into that data point. Sometimes I make a plot like this and it turns out that there's some coding error. I'm serious, like that I see a plot like this and say, these models shouldn't be so different on this data point. It actually turns out that there's been some data entry issue or something like that, or really there is a difference that makes more sense in terms of why there's a different thing, but you'd be surprised all the things you can find out by making a plot and saying, oh, which data point is that? So let me go. Sorry. To the last slide. The plots in this, all the slides you can make them all using this Bayes plot R package, and all the code is online. But I don't think they're necessarily the most beautiful visualizations in the world. They're not anything new, but just the idea of like looking at scatter plots of simulations from the predictive distribution, I don't know, I'd be surprised if you could find any papers with that in it until maybe like the past like couple of years or something like that. It's very, and I think the more that we do these things in like visualizations, the more likely it'll be that people will look at them and think about it, as opposed to getting buried away. But mostly these aren't necessarily things like pictures that, I mean, I do encourage you if you're publishing stuff to always show like the checks that you're doing, but even especially for people working in industry, some workflow. I think the biggest takeaway from this is that like at each step of that workflow, there's ways to be refining what you're doing, and you don't always need, for example, you can learn it so much and save so many resources just by simulating data, right? And saying not worth considering all these models because they're just a priori ridiculous. And that's often what happens when I do like consulting or something like that. I'll come in and just say, have you checked what kinds of data these models are actually capable of simulating? And the answer is almost invariably no. And it's just because that's not taught. But I think it'll save you a lot of time and headaches, and it'll save you trying to diagnose all sorts of problems after you fit the models. It's much easier to figure it out ahead of time than it is to figure out why it's not fitting well after you fit it. Right? And so there was more stuff in here than I got to, but anyway, I want to leave some time for questions, and sorry if I was talking quickly. Sorry, any lingering questions? Yes?
You were doing this in Stan when you did the sample?
Yeah, we fit the models and stuff in Stan, but all of the prior predictive simulations, so I just did them in R, right? You only need something like Stan to actually fit the model. Okay. But everything else is just, you could do it in R, Python, whatever, just the prior predictive stuff.
What kind of sampling algorithms were you using to figure out for that problem?
To fit the multi-level models and stuff? Yeah, the default like Hamiltonian Monte Carlo no U-turn sampler variant that's in Stan. But I mean, these models weren't particularly complicated. You could probably fit them in many different software. Yeah.
Thanks for the talk. Say hi to Andrew.
I will.
If you have historical data, do you still need to simulate your data?
Yes, sure. You mean if you actually have data points from a prior data generating process?
Probably a subset of your entire body. Maybe you had a subset of it.
Yeah, I think it's always worth simulating data, in particular because so there's things that are going on. There's different ways in which the model can be. There's different ways in which you can evaluate the model. So the reason to simulate data always is that at a minimum, the model should be fitting data that it itself generates, right? So in other words, if I simulate data from the model, then I fit the model to that data, and it doesn't fit, then there's something, the code, or I don't know, there's some, and it's always worth doing something like that, I think. So at a minimum, you can always simulate data from your model as like a consistency check that, right? You should be able to data, fit the model to that data, and basically recover the parameter values that were used in that simulation to some degree, depending on how many data points, how noisy the data is, more or less able to actually recover those values. And you probably need to do it many times if you want to actually take anything away from that. But that's something you can always do, right? If you use proper priors, you can always simulate data from the model. And Andrew Gelman and some other people have a paper, I think it's called simulation-based algorithm calibration or something like that. It's on, I think it was published, but it's definitely on archive, that talks about that procedure more formally, basically using simulating data from models and refitting the models to those data many, many times in order to do like a self-consistent, right? That should work. If it doesn't, then there's something wrong. But yeah, you can also, I mean, it's always useful to have actual previous data to use also, but I wouldn't say it ever rules out the utility of simulating data. That's a good question.
have strategies when you're modeling a latent variable, and in which case a lot of these posterior predictive checks look really funky?
Yeah.
That tell you what you want.
Well, sure, yeah, you can't really compare it to the observed values in that case. Yeah, that's harder. You can't directly check. I can't say, well, how well am I predicting the latent variables? Is not something you can say, but you can, but essentially, I don't know. I mean, one thing you can always do is say, how well is it predicting the consequences of the latent variables, right? You can't, I mean, you're gonna get predictive distributions for the latent variables if you're actually modeling them, but you won't be able to compare it to the observed values necessarily. But there should be some implications of the latent. They connect to the observables, right? And so, yeah, the only actual posterior predictive checks you can do is if you have like with something that's measurable, right? Not in the sense that you can actually observe it. Yeah, I don't know. You have to compare to the things that you actually can observe, but different ways of modeling the latent variables will result in different predictions for the actual observables. And so then you can differentiate between them in that way, at least. And you can also compare directly the predictive distributions of latent variables that different models make and see which is more consistent with whatever theory you're working with or something like that. So you have to kind of come at that question a little differently. Either look at the consequences, the observable consequences of them, or like how consistent those distributions are with what you know from other information. Hopefully that makes some sense, but yeah. I don't have any tricks for making them not latent anymore. That's a good question. Anything else? So yeah, I didn't get to some of the stuff in here, just this, but if you're interested in like the MCMC diagnostic visualizations and stuff like that, those are all in the, so in the vignettes for the Bayes plot package, it goes through basically what I was gonna probably say today about those visualizations, so you can actually read it and it will make more sense than I wrote it, so it'll make more sense than me just standing here speaking it. That's why that was the section I chose to skip. So yeah, if that does interest you, you can read those there. Thank you.